Diffusion is very interesting when it comes to modeling, actually. Okay, we can talk about actually the thermal energy, which is transferring on a thermal conduct. The objects that transferring heat on the other words, right? So the heat energy transferred by the thermal conduction. What does that means, right? So we'll talk about that, right? Thermal conduction. And within or between objects where the temperature gradient exists. So what this means is actually the heat. You can have one object or two objects or whatever which is touch each other. Uh, so when you burn something like this in this area, right? So it's heat transferred through this object, right? Okay, and the really hot area is this part, and then it will be eased down little by little, right? So that means what? So this area maybe you can hold, right? From here you can maybe hold for a while, but here it will be really hot. So that means hot to just cold. It changes its values, right? So this is what we call gradient. Okay, this is what we call gradient. So the important part here is, yeah, actually the heat is transferring from one point to the other, right? So that is the thermal conduction, right? Okay, and yeah, so this will happen in atomic level, actually. So so if you look at your object, whatever it is, and then there are atoms in between, this is how it's generated, this object. If these atoms are close enough, that will be too solid, right? If these are more further with the distance, well, it can have a liquid. If it is more distance, you can call it air, right? So whatever it is, whenever you produce some energy or heat in here, these particles start moving, right? So it will start moving, it will start vibrating and heat each other. All this happens, right? So that's how the heat is actually, temperature is moving from one place to the other. So why it is not the same level of heat here? If I call this hot, right, but here it is not that hot, right? So it will be less amount of heat when it's going through the area, right? So why is this? Why it is happening like that? So that is the reason is, whenever they start heat up, they get more energy to move. So they move, but they're hitting on each other. There's a collision, right? So there are atoms hitting each other. So because of that, there's an energy loss. So due to this energy loss, we say the diffusion of energy. That means one place is really hot, the other is not related that much hot related to the place that we have it, right? And that is the gradient effect. The gradient effect causing so diffusion of energy as well, because diffusion of energy causing the gradient effect. The diffusion energy happens by these collisions of each atoms. Okay, right? So what did I say? Okay, let me repeat it again. So there's a heat produced here, and that produce a kinetic energy which make these guys vibrate or move, right? So if you have more energy here, yeah, they are really hot, and then they start moving. So that is where the kinetic energy comes in, right? Once they're moving and hitting each other, that will consume the energy of this piece to this piece. So if this has more energy, there's energy consumption between two pieces, right? So that means yeah, he cannot move more, but he can transfer this energy to this, but not 100%, because it's average it out, and also the energy, the the collision causing a loss of energy. So because of that, it will be less energy for this one, so it is a less heat. So if it is really hot compared to that, this will be a little hot, right? So when it comes to the levels by levels like that, that's what we call gradient, right? Okay, so this is the idea of heating some object, and we're going to look at how we really thinking of modeling this thing, right? And what are the ways that we can condition this as the equations and all that, right? Okay, so I'm not going to go through all the equations of temperature transferring or the thermal dynamics. We'll talk about what are the assumptions, how we prepare the model, and what are the things that we have to consider in that case. Okay, right, so these are the assumptions here. So we start with the assumptions. If the surface, we take one piece of metal, so this is what we get to take care of this part, right? So we'll have the piece of metal like this, and it says, okay, the temperature of the top of the surface, so this is the top of the surface, and if I say 25 Celsius, right, and it will be every direction, so that means this surface has the same temperature at the beginning, right? So surrounding, if it is a room temperature, if it is still in the room temperature, immediately surroundings of this guy is also same as this bar. So that is the source. If you have some room temperature, or the object in a room temperature, it will be the same as the room. That's what it says. Okay, and we'll talk about the surroundings. Immediate surroundings are at the same temperature. That's what it is. Right, temperature diffuses within a bar, right? So within a bar we can have some different temperatures, right? But external conditions do not affect the temperature. Usually it is, right? So if you heat up here, one piece of here, right, what happens to the air around it? Well, it's getting heat up too, right? So in that case, there's the influence of the air around it to these pieces, right? Every area of this. So, and these areas also absorbing energy from the surrounding, right? So that means not only by the object, these are actually heating by surrounding air as well. But in this case, we ignore that and we consider only the heat source is the only one making it hot or cold or whatever. We don't care about much in the temperature around it. Okay, right, so how are we really going to handle this kind of a situation for our purpose of modeling, right? So what we do is we just divide the bar that we have into several cells like this. So they have so many cells now, right? And we divide this by n columns by m rows, right? So this is a different size of different number of rows and different number of columns that we have here, right? So this is one thing, and then here it is. We represent black, right? These things right here is hot, and then this one is cold. What does this mean? Well, we're going to heat up some cells, right? So these are the cells we're going to heat up, right? So how are we going to heat it up? Well, you can either if you want, you can set up some you can set up some have the candle or something like that, and then burn it there. Just go there and burn here as well, at the burn here as well, right? So it will be burn that, and then here we have cold, right? So this is cold right here, right? And yeah, so that's how we initialize this. we set up some cold area, maybe put a ice piece here or the ice cube, and set a candle or something to heat it up, and we're going to simulate this, so the how this is going to work. So eventually this part right here will be decreasing its energy because it's cold, right? And this part will share its energy around it, right? And the heat will spread, and this one also heat will spread. So eventually it will take care of the heat like this, and the cold will be taken care of cold like this, and then heat again will generate some of it right here. So in order to make it actually take care by, the control of these areas properly, that's why we just have the grid for this. So in that case, I can identify each of the cells here, right? So instead of atoms that we actually have to consider, we can get a group of atoms. We call it one cell, right? So this is the cell actually, and then we apply this heat transferring mechanism. Instead of atoms level, we go to cell level, which is we created our own, and then we're talking about that. So that is the simulation. That's how we're going to work on this. Okay, simulation. Yeah, you can include those as assumptions as well, right? But anyway, so this is an algorithm. I'm not going to push you much to understand this if you don't, because I had to be fair for the non-computer science students as well. But I encourage you to learn this. So it's a pretty interesting concept here. Right, so here what it says is function to return m and n grade temperatures. Cell will coordinates in the hot sites have the hot value, right? Value hot, and then you have cells with the condition coordinates with the cold sites have the cold value, and the other cells have the ambient. So that means the environment temperature. So what does this means is, yeah, I have the cold here and I have hot here, and the rest we consider as ambient, which is the environment energy or the heat. And then it says m and n are positive integers. Obviously I'm going to divide these to m and n, and all positive. And right, so then hot sites, cold sites are listed of coordinates of hot and cold sites respectively, and ambient and cold and hot and cold are global constants, and cold is less than, ambient less than hot, right? Obviously this is the order. And then an m and n grid of the value. So what you're going to return here is you're going to return the temperatures of each cell. Okay, right. So the algorithm start with we get ambient bar, right? M and n matrix, right, of ambient values, and we're going to apply one function. So what is this line right here? Basically the last line right here. What does that means, right? So what is this? Well, usually when you're writing programs, if you don't know, when the developers writing programs, right, so you can write one part of the program and you can write another part of the program, and we call these functions. These are functions, right? And we writing pieces of code, and then I just, instead of I'm writing everything here, I'm just writing it separate and called here. So this is what this line right here do. Okay, actually in this program, right, in this program initialization is what we do here, and then we're going to call some function to take care of the rest. So this is you may notice it is called apply hot and return, apply hot and cold, right? So this is what apply hot and cold function. So that means another piece of the program. In this one, what you do is you actually apply the values to the bar, right? And so of course we have to maintain the order, and it is the same thing that we were talking about in the previous up there on the initialization. It's the same thing. And here after that we say the grid of values described have above has been returned. So that is what we are returning, the whole bar. And algorithm on this is new bar is the old bar give some values to the new bar. So that means the heat is generating and then spreading through. That's the same thing as that we did here. Applying heat and cold actually. So this part we did not do up there. So assign hot every new bar in the cell with the coordinates of the hot side. So that means, yeah, so now I have to have a mechanism to figure out how we going to spread this heat. So if I have heat here, right, I should consider my neighbors get some portion of this heat. Not all the heat, some portion of it, right? And there are neighbors in everywhere here, right? Okay. But you consider only the ones which is, I'll consider only the ones which is really touch this. So you notice this one is not touching any wall of it. This one doesn't touch any wall of it. But these are actually taking care of this wall, and this wall. What does that mean? That means it's going to spread the energy from this one to the surrounding, right? All right, so that is the heat diffusion that we're going to look at, okay? And there are two scientists actually argue on this. One is called von Neumann neighborhood. So the von Neumann says, okay, so when you spreading the energy around surrounding particles or whatever, you consider only the north, east, south and west. So why? Well, you don't have to worry about this part right here, because there's not much connection between the heat of this and this, the heat of this and this, heat of this and this, so on. So it is not having much connection, right? So because of that, von Neumann said, okay, don't worry about that. Just take the ones which is important to you. That means whatever the walls that actually touching you, right? So that is a von Neumann model. But in the mover, on the other hand, he said, nah, you consider all eight surroundings, right? And apply equation for that. So there are two people talking about two different modules of heat spread, right? So in the diffusion we pick one and then we continue on working on that and see what happens at the end, right? So actually what we are doing here is we base our model of diffusion using Newton's heat law. Of course we have to use that. I will talk about that in a minute, which state that each of the temperature change respect to the time of an object is proportional to the difference between the temperature of an object, right? So what this means is if you talking about Newton's law, it says, right, Newton says this before. So if you have one object here, right, and I have a surrounding objects around it, right? So these are the objects I have surrounding it, right? So anyways, the heat is going to go to them, right? The amount of heat is going to go. Not all, because there's a collision as I mentioned before. So because of that, not all the ones going, but it is some of them will go one object to the other. It's the same case if you get a one metal piece and if you get a one grid, right, it will be the same case. So it will be the whole hot neighbors you have, you have fraction of this to this, right? So this fraction over time, actually the delta from delta t, we consider, I mean, the t from t to delta t, I mean, this is the last time. If you have the initial time is t, then after a little delta t time, right? And in this equation it says proportional, so the spread of the heat is proportional. So that means if I have heat on my this guy right here, right, and the other one is actually the relative to this one, so then you will have so this one is, let's say this guy is m, or the max big one, and this is n or h or whatever the value, right? So the heat of m, let's say, I would say m heat, right, is proportional to whatever I have here is h heat. So that means not the whole thing goes here, some amount will go there, right? And what are the patterns it will go? So the patterns is I mean, the patterns are nothing but that we saw earlier, these two, right? So these are the patterns of energy flowing through an object, and they're talking about that here, two-dimensional grid. One human neighborhood of site is set of cells directly north, east, south, and west, right? So that's all the von Neumann says. And the other guy said northeast, southwest, and then also the diagonals, right? Right. So okay. So then the Newton's law apply for this one, and then we going to check each neighbor's temperature minus the site temperature is the difference between these two, and then you multiply that to get the change of this. So what does this means? Well, let's read this first. So the Newton's law of cooling is nothing but the state of range, rate of change of the temperature of respect to the time. Okay, so in this this approach is pretty interesting, right? So what they do, what they're talking about here is actually when we have one cell, which I have, I would say, okay, this is my cell which is heating up right now, so I call it hot site, and then the temperature which is going to spread around it, so these neighbors going to get heat up, right? So all these neighbors going to get heat up when you put some fire or something on that site, right? So what it says is, well, the heat which is changing to, I mean, penetrating or spreading through to the neighbor is proportional actually. So that means a change of temperature, right, is actually proportional to what you, the difference, addition of the sum of the difference around you, right? So that's what it says. So that means this is equal to what? If I call this neighbor 1, if I call this neighbor 2, 3, 4, 5, 6, 7, and 8, right? And then what I'm going to do here is, what I'm saying here is, well, the heat in neighbor 1 minus the heat myself on this cell, which is a site, plus, right, plus heat of my next neighbor minus again the site, which is this one, plus so on until the heat of my 8th neighbor minus the site. So that's the difference between each of them, and this is what the equation says, right? I mean the Newton says. And then how I'm going to tally it up? Well, you can say, since this is the equation of proportionality, you can say this is actually equal to the constant time this is the constant time, which is a rate of this changing, and add all together. So a constant time, this whole thing right here. In other way, I can write this as this right here. Okay, so this means the sum of all. So the sum of all, I can write it as this, and this neighbor 1 2 3 4 5 is represented by I equals 1 to 8. Okay, and then difference of these. Especially, you have to consider one more thing here, which is this R guy is always less than 1 mostly. Okay, that is something that you may have to consider, otherwise this value is going up. So the difference will be sometimes exceed the value here, right? So that is not going to work. So it always has to be this temperature of this center has to be higher than whatever surroundings, right? So that is a fact, right? Okay, because of that you will have to consider how much this R is. Okay, and why is it the neighbor minus site? So what is this gives you actually? This always gives you a negative value, right? So why is that? Well, from here to here, the change in energy is less than the energy of the site, right? So the difference is always what? This is high, this is low. So that's why you say the change is negative value, right? Okay, keep in mind that is very important. This will always give you a negative value. Why? The neighbor's temperature is less than my hot side, so it will be negative value. Okay, right. Those are things that you should notice here. And then okay, so then the rest is very simple. I think this lecture don't have much more to absorb here, but it's only the concept here, right? So especially with the open books, I don't have much to ask here, but I'm testing your understanding anyway. One interesting part is, yes, of course, when you consider this temperature of the cell of myself, right, the energy of that is always higher than my neighbors, right? Okay, right. So because of that, when you calculate this, actually this give you negative value, right? So what does that means is, when you're having a hot site in the middle, and your neighbors always get less amount of heat from this, so it's never going to be higher than this. So that's the one fact it's pointing out here. Okay, and also this R is always less than 1. So especially in this case, we consider this R is greater than 0 and less than 1 over 8. So that means what? 0.125 means we have 8 sites around it, right? And one of these is 1 of 8. So that is what rate, the maximum number it can go is less than 0.128. Okay, so that is something that addresses here. Okay, right. So so it is controlling some parameters, so that is very important that you are controlling these parameters, and understand why is it negative. Well, the hot site is here, and then the other values will be less than that, right? Okay, so those are the points that are to emphasize here, and there are a little bit more. How do I optimize this equation is another one. Right, so now what I calculated so far is only the temperature difference. That's what the Newton's law said. That's the temperature difference. So how do I know what is the actual temperature in that case? Well, that is actually I'm adding the site into the change. So this is the change plus the site will give you the new value, right? So if I add the side to that side, obviously I have to add the side to the other side, right? Okay, so that is what I'm doing in this line, right? And there's a funny thing here is when I add this one, this equation I just showed you earlier, which is h1 minus site plus h2 minus site, right, plus h3 minus site, and plus and so on until h8 minus site. That's what it is, right? Okay, so this symbol means that, and we are talking about again the Moore's idea, right? So how many sites I have? 1, 2, 3, 4, 5, 6, 7, 8, right? So instead of I'm writing in this way, I can actually write this in another way. How I can write this? So I can write this site plus r, all this thing is the neighbor, right? And then I say minus, so this is what this is without this one, and I can write again I equal 1 to 8 site. Simply this guy is nothing but I have r here, nothing but this one is equal to r8 site. So that is 8 of them, right? And I have one site here and the 8 of them here with the r value. So because of that, I can write this another line, which is I can say site minus r8 site, right? Okay, that is this one and this one, and the other term itself r I equal 1 to 8 neighbor, right? So when I take the site out from here, I can put it here, and then I have 1 minus 8r right here. So this is nothing but this guy plus r neighbors value, whatever it is, and then the r is minus to this is nothing but 1 over 8, right? So that is the only simple simulation. With this equation right here, I can process and then let it run for a while and see what happens to the neighbors. So each neighbor of your cell will take care one by one until it's complete the process. Okay, so when you apply that, actually what you get is something look like this. So at the first time of t, your neighbors get less temperature. In this case it will be less and less because I'm having a cold here, and these guys are little positive values, but here these guys are less values than this one, so it is spreading like that, this one too. And the grid 2 after t2 time, it will be look like this. So you can see the gradients in it anyway, right? So that is the gradients means it's having a less or the higher values than this guy. This is cold, because of that these are considered higher. This is hot, because of this these are just less hot around it, right? And then you simulate it for a time and you end up with something look like this. So look cool, but that is what the gradient means, right? And then you can run this experiment and this is what you get. And then the equation you have to understand in this chapter is, how did I get from here to here? How do I get it from here to here? Unfortunately, yeah, the one thing is, it doesn't mean anything if I ask all these things as is, right? It's you just look at the notes and answer. But I like you to understand this, even it is very simple subject. I mean, today that we talk about diffusion. It is very important. Why? Well, this heat transferring thing that we can apply for a forest and things like that. So next time we're going to look at forest fire, how we really going to apply kind of a model like this to that. Why is it important? Well, in California you can have so many fires in each year, right? Yeah. So in this case, how do I actually handling those, modeling those, and see what causing and how it's damage everything, and how do you stop that and things like that. So that kind of a modeling is important on the fire spread. So we'll talk about that next time.